Okay, it's 1 o'clock. How y'all doing? Okay,
Good.
good. All right, so we're going to try and wrap up this section here, 10.5. And we covered half of it. Last class, we talked about lines and how we can formulate a new kind of perspective on lines using vectors and a vector equation for a line. And now we're going to talk about planes. And so remember what we had said was that to define a plane, we need 3 points, right? 3 points in space. Now, we are not going to formulate a vector form for the equation of a plane. We are not going to do that. We did a vector form or vector equation for lines. For planes, we are doing something different, okay? Later on in the semester, we will come up with a vector equation for a plane. We will, but it's not till chapter 13, okay? And we're in chapter 10. So you'll have to just kind of stand by for that. For now, we just want to look at planes and look at some very interesting properties of planes and how we can incorporate vectors, but we're just not going to have a vector equation. So, all right, with that said, let's go ahead and start our discussion of planes. So we've already seen in three-dimensional space that in order to define a line, right, we need basically a point and a direction vector. Okay, so when we're talking about lines, just give me a point and give me a direction vector v. Okay, and give me this point, and for that point, I'll just call that that's like my x naught, y naught. And so we come up with that vector equation, r of t equals r naught plus tv. Actually, that's r naught. Okay, so but basically you give me a point on the line, you give me a direction vector of the line, and I will be able to generate the entire line. All right. So for a plane, like I said, we need 3 points. So, oh, I should not have that there. So for a plane, I need 3 points, right? To uniquely define a plane, I need the three points passing through that plane. So we are going to start by first defining something on this plane called the normal vector. Okay, so every plane has a normal vector to it. And the way we come up with that normal vector, and just to show you what a normal vector is, you have a plane, and any plane you ever have sitting in space, you have a vector that is sticking out of this plane that is orthogonal to the plane, right? Every plane should have this. So if I tilt the plane this way, then my normal vector should be pointing out like this, right? Now, the normal vector could also be coming out the other side, but for every plane, I should have a vector that's orthogonal to the plane. Yes? Make sense? Okay, so the way we can come up with that normal vector, if we are given 3 points, is pretty simple. We just create vectors from those points. So remember, the points are sitting in space. If we just change those points to vectors, then those vectors are actually kind of coming out from the origin. And then what we do is we create vectors between these vectors, right? So we create this vector and this vector, and then we just cross them. So if we cross the 2 red vectors, we're going to get a new vector that is orthogonal to the plane. So it's a pretty simple construction to come up with that vector, that normal vector. So the normal vector is in purple, right? Does that seem pretty straightforward? Give me 3 points. I'll create these 2 red vectors. I'll cross them, and that'll give me a normal vector. So if you think about it that way, okay, if you think about it in the sense that every plane should have a normal vector to it, then in order to define the plane, you either need 3 points, or I could just give you 1 point on the plane and the normal vector. Do you agree that that would give you, that would define a plane uniquely? So 3 points would definitely give me a plane, but instead, how about I just give you a single point and tell you this is its normal vector. Then there's only one plane that can satisfy going through that point and having this as a normal vector. There's no other planes can be placed here and still have that point going through it and that normal vector. Does that make sense or not? Y'all are all kind of looking at me. I'm just trying to get you to see that our traditional thought is 3 points, but now I want you to be thinking normal vector in 1 point is all we need. And so that's what this note says. So just need a point on the plane and any normal vector to the plane that, obviously that means perpendicular to the plane. So if, let's say we have a point, x naught, y naught, z naught, and let's say we're given a normal vector, which we will use little n here for the normal vector, and we'll call that vector ABC, right? Then the equation of the plane is always going to be this. So I'm going to copy this. This is the equation that you should be familiar with because we talked about it last class. So all planes can be written in this form. Okay, so that's what we call our standard equation for a plane. I'll give you a specific example. What if I had 4x minus 1 plus 3y minus 4 minus 5 z plus 1 equals 0. So if I look at this equation, I have to recognize this is the equation of a plane. The way I know that is because it contains x, y, and z, and all the variables x, y, and z are all linear. None of them are squared, right? That tells you we're looking at a plane. So can somebody tell me right now what point lies on this plane? I mean, there's infinitely many points, but from looking at this, can somebody tell me a point that actually lies on the plane? Go ahead, anyone.
Can it be 4, 12, and -5?
4, 12, where are you getting that from? Oh, are you distributing this through?
Yeah.
What you're doing? Okay. So look at the formula up here. The x naught, y naught, z naught correspond to the point that's on the plane. Okay, so this is your point. And then the vector ABC corresponds to the normal vector.
Okay.
Okay, so looking at it that way, what would be a point, guaranteed point on this plane then?
1,
4, -1.
1, 4, -1. Just by looking at that equation, I can tell from this number, and this number, that point 1, 4, -1 has to be on the plane. Okay, it has to be. And then I also know that the normal vector for this plane would be the vector what?
4, 3, -5.
3, -5, right? Okay, so that was like your first example. Let me give you another example. Here's a plane written out the way that you've seen it written out. Something like this: 2x minus 3y plus z, let's say, equals 0, like that. Okay, so there's an equation of a plane, more like you would see like in college algebra. All right, can somebody tell me a point on this plane? It's a little tricky. I'll give you a hint. I could rewrite this as 2x minus 0 minus 3y minus 0 plus 1z minus 0 equals 0. Do y'all agree that that's the same thing?
Yeah.
Okay, so if I write it that way, then what's a point that's on this plane?
Just be 0, 0, 0.
0, 0, 0. So the origin, right, is part of that plane. And then the normal vector is just 2, -3, 1. Okay? So you didn't realize this before when you're in college algebra, that the coefficients on the x, the y, and the z, those coefficients always represent the normal vector, the components of the normal vector of that plane. College algebra, you're not talking about vectors, so you have no idea that that's what they represent. But that's what I'm telling you now, is that the coefficients on your variables make up the components of the normal vector of the plane. And then if there happens to be some numbers next to the x, y, and z, like up here, then that'll give you the actual point. Are we good? Okay. Now, back to the notes. So notice I said, notice this is not the vector equation of a plane. That'll come later, okay? Also notice that if we distribute the a, the b, and the c through this equation, okay? So if I distribute that a through here and here, oh, oops, and then the b through, and then the c through, the first things you'll get is like ax, okay, you get that, and then this b times the y gives you the by, and the c times the z gives you this, and then all the other distributions, a times x naught, b times, or a times negative x naught, b times negative y naught, every time you do those distributions, those are just numbers, aren't they? So like all of this is just a number, because a is a number, x naught's a number. B is a number, y naught's a number. C is a number, z naught's a number. So those all together should just be a number. So a lot of times we call that D, just D instead. And so this equation becomes this, and that's what we call the linear equation of the plane, okay? In other words, we've distributed everything through, there's no parentheses. And that's what you see in college algebra. All right. So we move on. First example here, we want to find the equation of the plane through these 3 points. All right, so I've given us 3 points, right? So who's going to lead us through this? I'll take a volunteer first, and then I'll start calling on people. Who wants to lead us through the procedure for this? Please don't all volunteer at the same time, please.
Well, first you have to create the 2 vectors, right?
Yeah, good, Caden. So Caden's suggesting that we need to create the 2 vectors. I agree. So visually, what's happening here is we've got our 3 points. Doesn't matter which is which. We can label them however we want. Do y'all understand what I mean by we can label them however we want? Because we're in 3-dimensional space. We don't know what our viewpoint is, right? Like we don't know where we're standing in 3-dimensional space. So it makes no sense to try and put these in any order, because you could be standing anywhere around the plane. So there's our plane. So Caden is saying, let's create 2 vectors. So what do y'all say we go from here to here and here to here? Those are our 2 vectors. All right. So Caden, will you give me the first one? I'm just going to call it this one U and this one V just for convenience. So Caden, you want to give me what U is?
Yeah, it would be -3, -7, and then -15.
I agree. Everyone see what we're doing there? Okay, and then how about David? Is David here? David C? I don't think David C has ever been here. Okay. How about Jared? Jared? I'm calling on people that haven't answered in the past first here. So Alberto? All right. Reagan? No Reagan? All right. Damien? How about Damien? Am I in the right class here?
Yeah, I mean, I'm not quite sure what to do, but I'm
I want
here.
the vector. I want the vector V. Give me the components of the vector V. So this vector here,
It-
what are its
It would
components?
be 12 minus 1, so 11.
Mhm.
and then -3 minus 2, so -5,
Okay.
and then 1 minus 114, so
Oh, that's one, sorry, that's one, that's a comma.
oh, okay.
Yeah, hold on. 1, 2, 14. So -13?
Yes.
Okay, good. All right, good. So Margie, what are we gonna do with these vectors?
We're going to get the cross product of them.
All right, we're gonna do the cross product. So let's go ahead and do this. Let's cross that with V, and we'll have to do that over here on the side. I'm gonna do I, J, K, -3, -7, -15, 11, -5, -13, and then we run our cross product. Now look, just so you all know, most of your graph, if you have a graphing calculator, a lot of them can do cross products.
Okay.
So I'm not going to go through during class and show you how to do it, but if you come to my office hours, or if you've heard of YouTube or Google, you can probably figure it out. There's ways, some of these calculators have them built in, like the cross product is a built-in function. And if you have an older graphing calculator, you can even write a program to do cross product. So if you're a CS major, that might be a fun little thing to actually program your calculator to do cross products. So anyways, as I'm talking, why don't you go ahead and calculate that? I'll see if I can't just do it. There comes a point where we don't want to have to do this by hand. It's kind of a pain in the butt. But I will show the mechanics of what we're doing here. So covering this up, and then 70, what is that? 70, 80, 91, take away 55. So take away 75, I believe. And then the middle one, cover it. So we're going to get 39. We're going to take away, what's that? But it's going to wind up adding because we have a minus. 165. All right.
I got a different number.
Yeah.
-204. Did I get that wrong?
Did you put them? Oh, you already put them together though, right?
Oh, I'm sorry. Yeah.
Oh,
Yeah.
yeah. Okay. Yeah, I'll do that in the next step.
Sorry about that.
No, it's good. And then here we got 15. Oh, we're going to have to change the sign on this one. Don't forget that. And then we have 15 and then plus 77. Okay. What's our final answer? We've got who wants to give that to me? It's just arithmetic. Daisy? What's our cross product?
16. The second one I'm not sure. Is it -204?
-204. Good.
Okay, and then 92.
92. Can we all get kind of a nod? Everyone agree on that? Yeah. Okay. So that is our cross product, which means this is our normal vector of our plane, isn't it? Okay. Abi? Did I say
I'm sorry,
that?
what was that?
I'm sorry, I barely heard you. You sounded like a robot.
Can you hear me?
I can hear you kind of, yeah.
What was the question?
Well, my question is what now?
Hear you.
Right, you're cutting out, so. I'll
Now
come
we
back.
write the equation.
Yeah, we write the equation. So why don't we just go ahead and jot down what the general form is. Right, this is the linear form, oops. The plane right here. Okay, so that's the general form. And this vector, right, the cross product, this represents our A, our B, and our C. And so all we need now is the x naught, y naught, z naught, right? So Abi, what do you want to use for x naught, y naught, z naught?
Could we use 1, 2, 14?
Yes, 1, 2, 14. But actually, it turns out we can use
Am I looking at the wrong?
any of
Okay.
them will work, okay? Any
Okay.
of these 3 points. So it's totally up to you. I'll stick with 1, 2, 14 because the condition of x naught, y naught, z naught is that it has to be a point on the plane. The fact that we drew our vectors coming out from that point doesn't impact that we have to use that point, all right? So I think we're ready. It's going to be 16 x minus 1, and then we're going to minus 204 y minus 2, then plus 92, and then z minus 14 equals 0. And that is the equation of the plane. Any questions?
Yeah, just one. So we got the -1, -2, -14 from our cross product.
No, we got it from this point right here. So this is x naught, y naught, z naught. And we just plugged them into this formula. So x minus 1, y minus 2, z minus 14.
Oh, okay, I understand. We got our ABC from our cross product.
That's right. Our A, our B, and our C, which wind up being the coefficients of x, y, and z, are going to be the normal vector.
Okay, thank you.
Got it? Now, this is correct, but you could also distribute through. And if you distribute this through, then you'll wind up with like 16x minus 204y plus 92z. And then you got a bunch of numbers to put together. So you got like -16, that's from here. What is that? Positive 408. And then here, I don't know, 92 times -14. Like minus 1288 equals 0. And then you could put these 3 numbers together. Okay, and that would just be a different form of the same equation, the same plane.
So if we would put the undistributed one on like a test, it would be fine?
That'd be fine. Yep.
And -1288 is D.
Negative what?
-1288, is that D, or is D something else?
No, D is all these numbers together. So those
Man,
3 numbers
sorry.
together, that's D.
Yeah, sorry, that's what I meant, sorry.
Oh, did you already put them together?
No, I was just, because I saw the one with no variable and I assumed that was D. I just didn't put them together yet.
Okay, yeah, so all these together is D. Okay, so the big thing here is this. If you have 3 points, right, that makes up a plane, and we should always be able to come up with the equation of that plane, just given the 3 points. Next question, or next idea. Okay, let's talk about the angle that is formed between 2 planes. So if you have 2 planes that come together, right? So if you have a plane and another plane, remember the planes extend in every direction. So unless they're parallel, right? Unless the planes are parallel, they are going to meet somewhere, right? 2 planes. And when they meet, won't they meet in a line? Their intersection will be a line. But the thing that we're talking about right now is, what is the angle between these planes? So when you look at this, here's 2 planes, right? We're trying to figure out the angle between them. So I'm going to kind of look at it from the side like this. Do y'all see that? When we're talking about the angle, we're talking about there's actually 2 angles you could say. There's like whatever this angle is, right? And that would be equal to this angle. And then whatever this angle is the same as that one. Y'all agree? So when you talk about the angle between the 2 planes, you're always going to be talking about the smaller of the 2. Okay, it'll always be the smaller angle of the 2. So the way we can figure it out is actually pretty easy. Does anyone have an idea? Well, it says it right here. the angle between two planes is the same as the angle between their normal vectors. Does that make sense? Because if I put the normal vectors of these two planes on here, okay, maybe you can see this. So the orange vector is the normal vector of the orange plane, and then the green vector is the normal vector of the green plane. And so whatever the angle is between these vectors should correspond to the angle between the planes, because aren't the vectors 90 degrees? Like they're rotated 90 degrees from the plane, but they're both 90 degrees from the plane. So if you rotate both of those 90 degrees, they'll be laying on the planes, both of them. So all we have to do is find the angle between them. And remember, vectors can be moved around. So I can move those normals around where they're both kind of going to the same point. And I think it's maybe a little easier to see from that perspective that that angle here should correspond to that angle here. Okay. Now, the question is, how do we find the angle between two planes?
We get the, isn't that the magnitude cosine theta?
Yeah, there was a formula, right? There was a formula. Let's go back. Let's go take a look. We had a formula back in 10.3, dot product. Oh, there it was. 10.3.6. If theta is the angle between two vectors u and v, then the following is true. Theta is the arc cosine of the dot product of the vectors divided by their magnitudes. Okay, that's it right there. So what we need to do is we need to dot the two vectors, and we need to take their magnitudes, divide that through, and then take the inverse cosine, and that'll be the angle between the planes. All right, nice. So let's do it. Let's do an example. Yeah. Okay. Well, you know what? Before we do this example, I think I can get through these other two notes because they're pretty obvious. Two planes are parallel if and only if their normal vectors are parallel. So the only way you can have two planes that are parallel to one another is if their normal vectors are also parallel, right? And parallel, remember it means scalar multiples, right? That's all it means to be parallel vectors. So if you look at the vectors, the normal vectors, and they are scalar multiples of one another, then what you can tell me is that those planes are parallel. Similarly, two planes are perpendicular if and only if their normal vectors are orthogonal. But that's easy for us to check, isn't it? We can always check to see if two vectors are orthogonal by just taking the dot product and getting 0. So that's just a visual of what's going on there. All right, so now find the angle between these two planes. So let's see, Lorraine, is Lorraine here? No, Lorraine. Oh, there you are, Lorraine.
Yes, I'm here.
What's going on?
Not much.
I think this might be the first time we've heard from you.
Yes.
Yeah, we've missed you. You doing okay?
Yeah, I'm doing good.
Okay, so I'm going to ask you now how we're going to proceed here. So how do you feel about that?
I'm not sure about how to find the angle between these.
Okay. So the note that we just covered said that the angle between two planes should be equal to the angle between their normal vectors, right? That's what the note said here. Oops. The angle between two planes should be equal to the angle between their normal vectors. So how about this? Can you tell me what the normal vector is of the first plane? So I'm giving you two planes here, and those are the equations. So Lorraine, can you tell me the normal vector of the first plane?
As far as like the coordinates of that,
The components of this vector, what are they?
just 1, 1, and 1.
1, 1, 1, right? 1, 1, 1. And Lorraine's just popping the numbers off here, right? That's it. Okay, and then the normal vector of the second plane is going to be Lorraine, go ahead. I mean, you understand it, obviously, so,
2, -4, and 7.
and 7, okay. And that's it, okay? Here's what we got. Now, we need to find the angle between them. So, Benjamin,
All right.
what is the formula that we're gonna use for this, Benjamin? Did you happen to write it down, or do you have it there?
Yeah, that was the in
There you
the arc cosine of
Yep.
u dot v over the magnitude of u and v.
Yep, so u dot v over magnitude of u, magnitude of v. But for us, I'm using n1 and n2, right? So I'm just gonna rewrite the formula. It's gonna be cosine inverse, let's just do it this way. n1 vector dotted with n2 vector, magnitude of n1 vector times magnitude of n2 vector. And we should be in business if we can do this, right? All right, so we need a dot product. Benjamin, do you want to give me the dot product and I'll move on to someone else? You want to dot those for me?
Yeah, 1 second.
Okay.
Should be 5.
5. Okay. Anyone disagree? Anybody agree? Yes, okay. So it's 5, good. We also need magnitude of n1. And we also need magnitude of n2. So let's see, moving on to Fabiola. Fabiola. No Fabiola? Okay. And let's see, Adam?
For the first one, it should be just 1
It's 1?
or square root of 3.
Square root of 3. Okay, so
Square root of
good.
3.
We do this, square root of 3. And then, so if anyone has a question on how anyone's getting these, please, this is the time to ask. Terrence, magnitude of n2?
Just calculating in my head, I think it's square root of 69.
That sound right, everyone? So it's gonna be like 4 plus 16 plus 49, right?
Yeah,
So we're just taking these components, squaring them, and we're gonna add them all together, 20. Is that 69? Did I do that right?
yeah, I think so.
Okay, yeah, root 69. All right, there it is. Okay, so now we get to plug this all into the formula. So theta should be equal to the inverse cosine of u dot v, which was 5 over root 3 times root 69. And well, we're gonna have to use our calculators anyway to do the arc cosine. So at this point, we need to determine, are we gonna give the answer in degrees or radians? So I'm gonna put my calculator in degree mode. The instructions did not say what to give the answer in, right? So I'm just make sure that when I give my answer, I'm gonna let you know that it's in degrees. All right, so here we go. Oh, I did not switch it to degree mode. All right, now I'm gonna do arc cosine. Anybody want to share what they got?
I got for degree mode 69.66.
69.66 degrees. So I'm going to put a degree symbol there. Did anybody happen to do it in radian mode? No. If you switch to radian mode and give me an answer.
I got a 1.22.
Something like that, 1.215 or something approximately.
Yeah.
So if we were going to give this answer 1.215, we would not write anything after it. it is understood that it's radians. All right. Now you could write radians next to it, but you don't need to. If you're going to answer in degrees, though, you have to put the degree symbol there. All right. All right. So there we go. We're done. We found the angle between two planes. I don't know about you, but does the math here seem pretty straightforward? I mean, there's nothing. This is just like multiplication, squaring, square roots. But it's actually pretty amazing what we're doing, right? You have two planes in three-dimensional space, and we're very quickly able to calculate the angle between those planes. It seems like it would be harder, doesn't it? Seems like this would be harder to do.
Yeah.
All right, so now back to the notes. All right, the line of intersection of two planes. Now, we just spent all of last class talking about lines, right? And vector equations of lines. So if two planes hit each other, right? If two planes intersect one another, then they intersect in a line, right? The question would be, can we come up with the equation of that line, the vector equation of that line? So what is it that you need in order to define a line, the vector equation of a line? What do you need? That's what I started class with today.
Point in a directional vector.
Point in a directional vector. Okay. So let's say somebody gives you two planes, right? So you have the equation of the plane sitting in front of you, just like the previous problem. Here we go. We've got these two planes, right? In order for us to talk about the line of intersection of those two planes, what we need to do is first come up with a point that lives on both of those planes, right? So something like, I don't know, in this picture, you know, we would have to find some point that lives anywhere on that line. And that actually is easier to do than you might think, because for me to find a point that lives on both of these planes, I just have to find an x, a y, and a z that satisfies both equations at the same time. So I could just start messing with numbers, and you'll see me do it in a minute, but it's going to be easy to figure out an x, y, and z that works with both of these. The harder thing is the direction vector. Where do we come up with the direction vector, right? The direction of that line. Well, here's the quick, easy way to do it. Remember, we know the normals of these planes, don't we? The normals of those planes, we know them because they're just the coefficients x, y, and z. So we know them, right? We know those vectors. Now, let me do something with these vectors. Because they're vectors, let me move them so that they both touch that line of intersection. Okay, so all I did was translated them. Now I'm going to cross them. I'm going to take their cross product. And do you agree that if I cross them, the vector that pops out should be in the same direction as the line of intersection? Y'all see that? That will happen every single time. If you have two planes, you take their normals and you cross them, you get a vector that is in the same direction as the line of intersection of the two planes. And so we have exactly what Benjamin said we needed. Well, we still need to find the point, but the direction vector is going to just be simply crossing the two normals. That's pretty awesome, huh? I mean, that's, again, it's not a whole lot of work that we have to do. We just need to know how to execute it. All right, so let's do it. Are those the same two? Yeah, those same two planes. So for this one, find the vector equation of the line that represents the intersection of these two planes. All right, so what am I gonna do? Let's find the point first. Let's find the point of intersection. Let's just find a point on there. Anybody have any idea how I can go about this? How many equations do I have?
Two
Two
equations.
equations.
How many unknowns?
3.
Okay, that means you should have an infinite number of solutions. So what we're going to do is you just get to pick whatever you want. Pick any value you want for any of the three variables and make it a nice value. Like pick smart here.
0,
For what?
X.
Okay, we're gonna let X be 0. All right, that's Daniel's suggestion. Now, if you want, you could let Y be 0. You could let Z be 0. You could let X be 3. You could let X be pi. You could let it be anything you want, but 0 makes the most sense because it kills everything off, doesn't it? So let's let X be 0. Okay, if we do that, let's look at the first equation. It becomes Y plus Z equals 5. And the second equation, if we let X be 0, becomes negative 4Y plus 7Z. Let's move that negative 10 to the other side, 10, like that. Okay, so now we have a system of equations, but it's only 2 equations and 2 unknowns now, so we should be able to solve it. So I'm going to multiply now by, hold on. I'm going to do elimination. I'm not sure how you want to solve systems of equations, but I'm going to solve this by multiplying the top equation by 4. And I'm going to do that so I can make the y's cancel. Okay, so we got 4y plus 4z equals 20. And then negative 4y plus 7z equals 10. Didn't do anything to the second equation. Now I just add straight down. So I'm going to get 11z equals 30. And then divide through by 11. So 30 over 11. That's what z is. Once I know what z is, I can go get y, right? And I think I'll go grab my first equation here, and I think that's the one I'm going to work with. So I'm going to say y plus z, but I know z is 30 over 11, must be 5. So I'm going to subtract 30 over 11 on both sides. And you get y is equal to, let's see, I need a common denominator. So 55 over 11 minus 30 over 11. What do we have there? 15? No, 25, sorry. Over 11. Remember, watch my arithmetic. I screwed up at the end of class last time, didn't I? So I have x, y, z. So that is a point, isn't it? That is the point 0. Make sure you get these in the right order. 25 over 11 and 30 over 11. That is a point that lives on both planes, right? That point should be on both planes. So it is a point of intersection of those 2 planes. So if somebody else would have said, hey, let's start this by doing z equals 0, they'll get a different point, right? If someone said let y be 0, they'll get a different point. But it doesn't matter. The equation of the plane will still work out the same, which is kind of amazing, but it will work out the same. All right, here we go. What's the next thing? I have a point. Because we wanted the vector equation of a line, Benjamin said we need a point on the line. We got it. Now we need the direction vector of the line, right? Which you get by doing what?
You cross the normal vectors.
That's right. So we're going to now get the direction vector, right? So I should have said this from the beginning because this is one of the things I'm really trying to stress to you is when you're reading one of these problems, write down what you're trying to find. You're trying to find the vector equation of a line, right? You're trying to find this. That's the vector equation of a line. What we just did was found R naught, which is going to come from that point right there. We're going to convert that point to a vector. What we still need is the direction vector V, right? And that direction vector V is going to come from taking the normal of the first plane and crossing it with the normal of the second plane, which for us means we're going to take the normal of the first plane, 1, 1, 1, and cross it with the normal of the second plane, which is 2, negative 4, 7. And so we have to do a cross product, right? And I may not have enough room to do it right here. I'll squeeze it in. Does anyone have any questions while I'm writing this down?
For a vector with 4 dimensions or 4 components, can we cross that as well?
Yes. Yes. I
So
would-
we just need more than 2 dimensions to cross our vectors?
yes.
Okay,
No, you can do a cross product of 2-dimensional vectors also, but it's basically it's just a determinant. That's all it is. It's let me show you. I'll show you after this. Well, maybe if I have
Okay.
time, I'll show you how to cross 2 vectors, 4-dimensional vectors. I can show you how to do it.
okay.
Okay. All right. So here we go. We got to cross these. So I'm gonna try and do this faster. 7 plus 4, so 13. You just tell me if I'm wrong. 7 take away 2, that's 5, -5. 4 take away 2, -6. Y'all get that?
7 plus 4 is 11.
Where? 7. What did I do?
Put
Oh,
13.
it's minus. Yeah, minus. Hold on.
What? No, the 7 plus 4 is 11, not 13.
The first.
Oh, the first
number.
one.
Yeah, the X.
See, I'm not kidding around. When I said that my brain doesn't do arithmetic, just stop doing it, and just stopped. I'm not sure why. 7 take away 2, that should be 5. So -5 here, right? Do we agree with that? All
Yeah.
right, here we go. We're done. We just need to put it together, right? So we just use the standard form R of t equals R0 plus t times the v vector, which we just found. This is v. So R0 we get from the point. So that's 0, 25 over 11, 30 over 11. That's a vector plus t times the direction vector, which is 11, -5, and -6. That would be fine. That's an answer that is correct, but I could also maybe combine those together. So I mean, distribute the t through and then add the vectors. And if I do that, I'll get the vector 11t, and then I'll have comma 25 over 11 minus 5t, and then 30 over 11 minus 6t. That's the way that I like to look at vector equations of lines. I don't like it written as 2 vectors. I like it to be put together into at least 1 vector. Any questions on what I did there? All right, we're done. We're done. Now, I'm going to go back to my notes here. And I don't know, did I tell y'all that I wrote the little code to make all these happen? Did I tell y'all that? I don't know if I told y'all that. Okay.
Yeah, you told us.
Okay, so I want to just show you that when I wrote this, I had to draw that line, right? I had to draw this blue line. And if I show you the blue line right here, is this it? Hold on. Yeah, this is it right here. Three, am I not using, hold on, I may have used a different. 2x plus y plus z equals 6. That's not the plane we had, is it? That's not the plane we had?
No.
Sorry, I thought I used the information from that example. I thought I used this information to draw that, to do this problem, but it's not. They're 2 different planes. Never mind, I apologize. But I'll tell you, the way I did this is I came up with two planes. Here they are. I came up with this plane, which has a direction vector of what? Or sorry, a normal vector of what?
2, 1, and 1.
2, 1, 1. And then I drew another plane. This one has a normal vector of what?
Also, 2, -1, -1.
2, -1, -1. And then what I did is I just on the side, I did a cross product. You know, I found a point of intersection. I came up with the vector equation of the line. And this is basically the vector equation of the line right there. Sorry, I thought it was going to match our answer. That's why I was going to show it to you, but oh well. Okay, moving on. Distances. So this is where we can really start to see how we can use what we are doing right now to figure out some really cool stuff. All right, so distances. What if we wanted to find the shortest distance between a point and a plane? Okay, shortest distance between a point and a plane. So initially, that may sound like an easy problem. You know, like if you take the ground, okay, let's say that's the ground, and then I give you the point up here. I give you the point, let's say that's the point 2, 7, 13, okay? Then the shortest distance between that point and that plane would just be the perpendicular dropped down to this plane, right? Imagine that that's like a little right angle coming down to this plane. That should just be 13, shouldn't it? If that plane is lying on the ground, then the distance there should just be the z coordinate of the point, right? Yeah. But generally speaking, if I give you a plane that's just in arbitrary space, right? Tilted, just sitting somewhere, and then I give you a point and say, find the shortest distance between that point and that plane, that is much more difficult to do because it's not just the z coordinate or just the y coordinate or just the x coordinate. There's a lot more going on here because the plane could be shifted or tilted. So this is actually, at least at first sight, this looks like a very difficult problem. So here it is. Here's the plane, here's the point. Okay, so I'm gonna fix a plane in space here. I can't tell where I am. There we go. Okay, so there we go. We've got this plane sitting in three-dimensional space, and we've got a point sitting in three-dimensional space. And what our goal is to find the shortest distance between that point and that plane. So watch the way we're going to do this. Now, you have to keep in mind, what are the two things that we are given at this point? We have to have been given the point, okay? And we have to be given the equation of the plane. Once we're provided with that, the question is shortest distance, find it. So here's what I'm going to do first. I'm going to pick any point on the plane. Boom, there it is, okay? Any point. Now that should be easy for me to do because if somebody gives me, let's say, the equation of a plane, I should be able to find like a point on that plane by just playing with these numbers. Like here's an example of a point that would live on this plane. Do y'all agree that that point lives on this plane? If I replace x with 10, y with 0, z with 0, that works, right? So that's what I'm going to do first. I'm going to just pick a random point on the plane. Next thing I'm going to do is create a vector that goes from that point to that point. I should be able to do that now because I have 2 points. I can always create the vector that goes from one to the other, right? So that should be just a quick computation. Then what I'm going to do is I'm going to take a look at the normal vector of the plane. So the normal vector of the plane is sitting around, right? Sitting somewhere. Now don't get confused here because this vector could be anywhere, right? That normal vector of the plane, it's just that it's orthogonal. Agreed? Doesn't have to be, that normal vector does not have to punch through that point at all, right? It doesn't have to. Okay, now what I'm going to do is I'm going to slide that normal vector to where it does punch through that point. And that I can do because normal vectors can slide around, doesn't change them. This is just for visual reference. So here, oh, sorry, hold on. I shifted the wrong one. I'm going to leave the normal there. I'm shifting this vector over to where it touches tail to tail. All right, so just slide that blue one over. With me? Can anybody tell me how I can figure out this distance now?
Projection.
Projection. All I have to do is project which vector onto which vector.
Blue onto red.
Blue onto red. So remember when we did vector projections, it's been a while. When we did vector projections, what it was is if you projected the blue onto the red, you're basically dropping a perpendicular down. You see that? You're dropping this perpendicular down from the tip of the blue down to the red one, but that right there, right, that right there is the distance we're looking for. We are actually looking for that right there. So remember, when we did projections, there were two different things. We had a projection, and there was another thing we had. Projection gave you a vector, and then there's this thing called the component, right? So it was projection, there was a formula for it, and there was another thing called the component. And the component gave you the length of the projection vector. That's the one that we want. But to save us all some time, here is everything I just said in words, okay? It's like, okay, we're given a point, we're given the equation of the plane. Okay, we pick a point, we just randomly get a point, and then we create a new vector that goes from the point that we're given to the point that we just made up. Once we do that, we note what the normal vector of the plane is. And then what we're going to do is we're going to project the B onto the normal. And we're going to be looking at the component of it, which is the length of it. And that should be the distance. And that just turns out to be this formula right here. And that's the one I'm going to use. I'm not going to use this one, because this is easy. I think this is easier to remember. So we're just going to dot the normal with the vector B, find its magnitude or absolute value, and then we're going to divide that by the magnitude of n. Again, such a simple formula for such a complex idea. Seems to be the theme here, doesn't it? So find the shortest distance between these planes. You know what the most common incorrect answer I get on this is?
I have no idea.
I get two answers for this that are the most common, like, wrong answers. One of them is 15. And all that is someone looked at it and said, oh, 5 and 20, just the difference between those values is how far apart the planes are. That's one thing I see students do. And then another thing I see students do is they divide everything here by 2. And then they say, okay, 10 and 5, so the distance must be 5. And both those answers are completely incorrect. Because that would be correct if these planes were actually flat, like the ground and then a plane above it, but that's not the case. So we have to go through this, all right? So how we can do this? Find the shortest distance between these planes. Wait a minute, hold on, did we mess up? Because the note said the distance between a point and a plane. I'm asking you for the distance, the shortest distance between two parallel planes.
Well, if they're parallel, then the distance between the two is absolute no matter where you stand.
Okay,
So we just have to pick a random point for either one of these equations that satisfies them, and then find the distance from that point to the other plane.
exactly. Good, Daniel. So what Daniel's saying is the problem that I gave you a point and a plane, right? But if there's another plane up here, right, like this, then we could pick any point on that plane. Let's say it's that black one, and then just do the same thing. Okay, just do the same thing. Good, good. So let's do it. So one of these planes is going to just give us a point, right? One of these planes is just going to give us a point. The other plane is the one we're going to use to like create, use the normal vector and all that stuff. So just for simplicity, I'm going to use this one for the point. So that's this plane sitting here. I'm just going to pick a point on it. So I don't know. I like the point. I don't know. I'll let somebody. How about, let's see, Daniel's already answered. How about Jorge? You want to give me a point on that plane?
I think we found one last problem, and it's 0, 25 over 11, 30 and over 11.
Oh, you're trying to find the intersection, a point of intersection, but you have to be careful. These two planes are parallel, right?
Yeah.
So they don't intersect. I'm just asking you to give me any X, Y, and Z that will satisfy this equation, and it's completely up to you.
Okay, how about 0, 2, and 3?
Fine with me. Are y'all okay with that? Okay, so we have a point on that plane. All right, now on the other plane, I'm going to say that one's this one. I am again going to find a random point. And I'll let Donald give us whatever point Donald wants.
We can do 1, 0, and 2.
1, 0, 2. What do y'all think? That work?
No.
It has to satisfy this one. Hold on. We're trying to satisfy the second one.
We do 1, 1, 1.
1, 1, 1. That'll give us 2 plus 2 plus 2 is 6. We need to be 20.
Oh, it needs to be 20.
Yeah. Keep it simple. Make 2 of them 0. Make y and z 0.
Y and z 0, so 5. 5. What dx is 5?
10.
Or 10. 10.
10. Stressing you out, I think, Donald.
Sorry, I kind of got a little lost in here.
Okay, so we have 2 points, right? A point on each plane. Now, this blue plane is the one I'm going to work with, okay? This is the one I'm going to work with. So back with this picture that we had, the blue plane is actually this one, okay? And the black plane, we picked a point off it, is going to be that point. So this is kind of where we are with things right now. We have a plane and a point. We have a plane and we have a point up here, and we've chosen another point on this plane. And now, Juan, what do we do? Juan, no Juan. Maribel? Hey, Maribel. So what are we gonna do with this at this point?
Oh, I'm not sure.
I'm sorry?
Oh, I'm not sure.
Not sure? Okay. Let me go back to this. We had the point and we had the plane. We picked a point on this plane, and then we need to create a vector that goes from here to here. Okay? So can you create me the vector that goes from here to here? Tell me what that vector is. And we're going to call it B.
So, 10, -2, and -3.
Other way around. We're going from here to there.
-10.
-10, 2, 3. Okay. Everyone got that? Okay, next thing we need is Ezwa. What do we need now? We got this vector. Now we take that normal, right? And we will move that vector and we will project, right? So you're on mute, by the way. So
Oh my gosh.
it's okay. So yeah, I'm sorry. You were probably telling me what to do there. So you get the normal of this plane, right?
Right.
Okay. And what is that normal? I'm going to call it N.
Of the bottom plane, it'd be wouldn't it be 2, 2, 2?
2, 2, 2. Okay. Now we have to project which vector onto which vector, or we're actually doing the component. So we're doing the component of the B vector onto the N vector. But I told you, and we need to take the magnitude of this, but I just told you that that will be, oops, that will just be this formula right here. Magnitude or absolute value of the dot product of the two over the magnitude of N. So this is going to be dot the 2, take the absolute value, and then divide that by the magnitude of n. So this should be pretty straightforward now. It's just computational, right? All right, let me see. Reagan's not here, right? Reagan's not here. Alberto, Jared, David, no? Okay, so we're back. We've gone through everyone, I think. So can someone want to just to volunteer to give me what the top of this is at least?
Is it positive 10?
I don't know, is it?
If I
Y'all agree?
dotted them correctly, then it is.
Okay. Y'all agree?
It's absolute values 10 either way.
Yeah, the absolute value should give you a positive, so.
Well, I got negative 10, but I took the absolute, which then gave me, the dot product was negative 10. The absolute was 10.
Okay,
Just to
great.
make that clear.
Yep, good, good. And then someone want to tell me what the denominator is, magnitude of n?
Got square root of 12.
Square root of 12. 4 plus 4 plus 4, take the square root. And that's it. Wow. Again, I feel like we can't understate the simplicity of the math in terms of the calculations relative to the complexity of the problem, right? You walk in here and I'm like, hey, here's two planes in three-dimensional space. Hey, they're parallel. What's the distance between them? That's a very difficult thing to do without all of
I'd
this.
imagine.
Right? Yeah, I mean, if you try to do that with just the tools with no vectors or anything, have fun.
I can't imagine
have
what
a-
the proofs of this look like.
I have a
What-
kind of an off-topic question.
Yes.
Is this still Newton and Leibniz, or is this recent? Because I can imagine it'd probably be really difficult back then.
Well, no, the part of calculus that was developed by Newton and Leibniz was the differentiation and the integration. What we're doing now is just see, because right now we're not doing calculus right now, right? I mean, we're in a calculus class, but we're not doing calculus yet. We have yet to differentiate, right? We have yet to integrate anything. What we're doing is building up the foundation of three-dimensional space so that, see, what's going to happen later is that we're going to have something like, you know, a surface in three-dimensional space, and we're going to try and stand on that surface. I talked to you all about this before, I think first day, you know, and I said, you know, if we just like drop a ball right there, like which way does it roll, right? Well, instead of having a tangent line, we actually have a tangent plane to that point. You don't have a tangent line, you have a tangent plane. So it's almost like, you know, if you take a basketball, right? Take a basketball and then put a plane on top of it, right? Then that plane right there at the, I guess, north pole of the basketball would be a tangent plane, yes? Well, we can't be talking about tangent planes and shit like that if we don't even know how to draw planes or how to come up with, you know, normal vectors, and you just can't mess with planes and or anything else until you've got all this stuff out of the way. Okay. All right. Moving on. So that is how we find the distance between a point and a plane. Next idea is finding the shortest distance between a point and a line. A point and a line. So remember, this line's in arbitrary space, right? You've got this line, goes in every direction, right? And you've got a point, and you're trying to find the shortest distance between the two. Again, not an easy problem in three-dimensional space. Easier in two-dimensional space is not so bad, right? If you think about it, if we are on a flat sheet of paper and I draw you a line and I draw you a point somewhere, you should be able to find me this distance because you could probably do some geometry here, right? You might be able to like I don't know, pick a point here and like draw me a right triangle and maybe just, I don't know, as long as you can figure out what this side is, like this distance and that distance, then a squared plus b squared is c squared. You might be able to get it, right? You might even be able to do something with trig functions. But that's on a flat sheet of paper. If we take it off the piece of paper, it's a little different because, well, you have a z coordinate, right? So everything's going to be different. But we have a way of doing it, all right? So here's the construction of this one. So remember, we are given a point and we are given the equation of a line. Okay, that's given to us. Now what we need to do is find the shortest distance. So here it is. Here's a point and here's a line. Now it looks like it's on a flat sheet of paper, but imagine that this could be drawn any way you want. Okay, there's your point P and there's your line. And this is in three-dimensional space. So here's what we're going to do. We're going to pick a point on the line. Can we do that easily?
Yeah.
We have the equation of the line, right? We have that. So we should always be able to find a point on that line pretty easily. I forget who did it last time. I think it was Fabiola, but she's not here. I think Fabiola was the one who told us like pick t equals 1 or 2 and that'll give you a different point. Anyway, we know how to get points off of lines. So there, boom, we can come up with a Q, no problem. All right, now another point, okay, a second point on the line. We should be able to do that, right? And then we can create a vector between them. All right, now we can create a vector going from Q to P. So we've got this other vector B, and we have this vector B and this vector A. The distance we're looking for is this distance right here. Do you all agree? However, just using basic trig, if we call this angle theta, sine of theta by definition would be this side over this side, right? Opposite over hypotenuse. So it's just sine of theta is d over this, yes? You all agree with that?
So we're just using SOHCAHTOA?
Yeah, SOHCAHTOA basically, right? But I'm not done. I'm not done. We need to solve this. We need to solve this for D, don't we? Right? So let me solve this for D. D would be magnitude of B sine of theta. Agreed? The distance we're looking for is just magnitude of B times sine of theta. Now, do we know the magnitude of B? We could find it, right? I mean, we could find it because we came up with Q and then we can always create that vector and then we can find its magnitude. So finding the magnitude of B won't be a problem. Now, we need sine of theta. Do we know theta? Not directly, right? Not directly, but could we find the angle between these two vectors?
Yeah, because we have those two vectors.
Yeah, we have two vectors, so we could, right? So it seems like we have a path here, right? We have a path to get here. But this is what I love about math. Check this out, man. I never get sick of this. Here's where we are, right? Do you agree that algebraically, these two are the same thing? So all I did was said, hey, let's just slap a magnitude of A right there and divide by magnitude of A. And you're like, what? Why would I do that, right? Like, why in the world would I do that? Because, well, I didn't make this up, okay? Because, what is this? It's the magnitude of the cross product of A and B. That's all it is. This is weird because if we do this, look at what we've just done. This still blows my mind. I can't get over it. We're here. In order to solve the problem, we need to know the magnitude of B, which shouldn't be a problem, but then we need sine of theta, which means we got to go figure out what theta is. But just realizing that if we just very cleverly, is that a word? Insert a magnitude of A over magnitude of A, just out of thin blue air, thin air, just pull it right and just place it here and here, then we've created the numerator as being the magnitude of the cross products. And what that does is it eliminates theta from the equation completely. And so in order to calculate D, all you have to do is be able to come up with the two vectors A and B. And as long as you can cross them and find magnitudes, you're in business. It's amazing, I think.
So we don't even have to find the angle at all, or use
Nope.
sign, just only
Nope.
vectors?
That's just vectors. In fact, look, this is even crazier. What I'm saying to you with this formula is that D should just be the magnitude of A crossed with B divided by the magnitude of A, right? That's what D should be. Now B, we have to figure out B on our own, right? We have to come up with this point. This point's given to us, so we have to come up with that point Q and then create the B vector, right? The A vector though, is actually a vector that's on our line, isn't it? It's on our line. So couldn't we just not use A and use V? Isn't V the direction vector of our line? So we don't even need to come up with A. If they give us the vector equation of the line, we can just use the V as our A, which would change our formula to this. Which means if we do this way, where V is the direction vector of the line, then we only have to come up with one thing, and that's just B. And just plug everything in.
You're saying if like V is provided, that they say V is the direction vector of this line.
Yeah, remember this, we started with this. If somebody gives you a point and a line, right? Then what's the shortest distance between them? Well, if we're given the equation of the line, then we can come up with the direction vector, right? Let's do an example, you'll see. Find the shortest distance between that point. So we're trying to find the shortest distance between that point and the line that goes through this point, these 2 points. So we have 3 points. We have, let's say, the point that we were given here. That's the point 3, 6, -7. We're trying to find the shortest distance between that point and the line that goes through that point and that point. Okay. So in order to do this, we need 2 things. We need the vector that goes from any point on our line to the here. That would be our B. And then we need the vector that connects those 2 points together here. This would be our A, or if you'd like, you could call that V because it's also the direction vector of the line. Once you have those, you're ready to go to the formula. So we'll start over here. Caden, can you give me B?
B is 3, 3, -2, or -12.
-12, okay. And then let's see, how about, I'll use V. How about V, Damien? Wait, did I call on you, Margie?
Not yet.
I had
So,
you down, I don't know why.
oh,
Okay, go ahead, Margie.
okay. So you would like, you're looking for A or call it V.
We'll call it V. Yeah.
So the V vector would be -4,
Mm-hmm.
6,
Yep.
5.
5, sounds good. And now we just need the formula, right? So D will be equal to the magnitude of cross these 2 vectors. And then magnitude of V on the bottom. And by the way, it doesn't matter if you do B crossed with V or V crossed with B because we're taking the magnitude. We learned that cross products, you can't switch the order. But we did say that if you do switch the order, they're just going to be off by a sign. So when we take the magnitude, it's going to make that irrelevant. All right. So we got to cross these two. Let me go ahead and do the cross here. I'm just going to try and do it here. So 15 plus 72, I believe. Hold on, let me see. 15 plus 72. 15 minus 48. Then I'll make that pause to change it. And then covers 18 plus 12. Negative 33, but 33. Someone's going to have to check my math on this. 20, 30. I think this is right. Anyone get that for the cross product? Or did I completely mess that up?
I'm just not sure which way you should cross it. Would you get the same number, but just if you do it a different way? I mean, do it the other way, crossing.
I did it the other way and I
B,
got
it'd
all
be
negatives.
negative.
Yep, you'll get all negatives. And that comes from the idea that A crossed B is equal to the negative of B crossed with A. But again, because we're going to do the magnitude in the formula,
Oh, it doesn't matter.
it doesn't matter. Right? But you did get those numbers, right? Just opposite signs. That's okay. So I've got it. I'm going to do this on my calculator. I'm going to do 87 squared plus 33 squared plus 30 squared. And then I'm going to take the square root of that. So on the top, I'm getting 97.765 about. And then on the bottom, I take the magnitude of V, which should be pretty straightforward. Does anyone need clarification on where I'm getting these numbers from? Approximately 11.14. Inches, miles, light years, whatever the unit is, we don't know what units we're using here, so. There it is. Okay. Any questions? I believe that is going to conclude 10.5. Yes, it does. So I'm going to send everybody something. I'm not quite sure how I'm going to treat this yet, but this is what I'm going to send you all today. It might be later today, but I'm going to send everyone this. It's going to be an assignment, okay? And, you know, I think I'm going to count this assignment as one of the mini exams. All right, remember you get 8 mini exams, you have to do 4. I think I'm going to make this one of them. I just don't know if I'm going to call it mini exam 2 or not yet, but I'm going to send it to you. I want you to look at it. If it looks like something you want to go after, then you can get started on it. This worksheet covers nothing but 10.5. All right. And the way this works is I say here, you know, in terms of finding vector equation of lines, there's 2 main topics in this section, right? Lines and planes. When it comes to vector equations of lines, here are the things that I think you need to be able to do. You need to be able to find the vector equation of a line given 2 points on the line. So if someone gives you 2 points, can you find the vector equation of the line, right? Everyone should be able to do that in here. And then I just go through and I list out all the different things that I think you should be able to do. And then after that, I give you an example of each one. And these are the problems that I want you to do. There's examples A through J. Okay. Now let me show you, this is not as straightforward as you think it is. All right. So look at this first problem. The concept here is finding the vector equation of the line given 2 points. But look at the problem. Find the vector equation of the line through the center of this sphere and the point on the z-axis closest to the center of that sphere. Okay, let me run through that again. Find the vector equation of the line. Oh, why am I not writing? Uh-oh, my thing's not working. It's okay. I saved myself. Well, you know what? Let me see if I can get this thing to go again. I don't know why it doesn't want to write. Okay, who cares? I'm just going to have to stick with this. Find the vector equation of the line, right? So that means you need to come up with that R of t equals R naught plus TV, right? That couch potato formula. That's all you need and you're done, okay? If you can come up with that, you're done. Which means that you need, I think Benjamin started class with this, right? If we need the vector equation of a line, what do you need? You need a point on the line, you need a direction vector, right? Okay. But here's the thing, the 2 points I'm giving you are not straightforward. The first point I'm giving you is the center of this sphere. So you better know how to look at that and tell me what the center is. That's one of the points on your line. And then the other point is on the z-axis, which is closest to the center of that point. So it's like, here's the picture. You have a sphere. You're trying to find the equation of the line that goes through the center of that sphere and a point that is closest to the z-axis. The point on the z-axis that's closest to the center of the sphere. So yeah, do you see this is not as straightforward as just me giving you 2 points? You're gonna have to think about this, and they get harder. They get much harder. Okay, let me see this next concept. Find the vector equation of the line through a given point, but parallel to some given line. So again, you're just trying to find the vector equation of the line, but I give you a point and then some line that's parallel to it. So here's the problem. All right, so I think what I'm going to do here at this point is I'm going to give you one problem right now for y'all to work on for the rest of the class, just so you can get a feel for what this is really like. Let me just pick one. Yeah, that's a good one. Write that one down. We only have like 10 minutes left, but I think I'd like to put y'all in groups just so y'all can see if as groups you can figure out at least the approach to this problem. Like, how are you going to go after it? What would be your kind of path, you know? And I recommend when you're sitting here trying to figure this out, like get like a piece of paper and a pen and try and like visualize what you're trying to do. That really does help. Does everybody have that written down?
Yeah.
Find the equation of the plane. What do you need to find the equation of a plane? I don't know. You'll have to talk about that. Okay. But that's going to conclude it. So we're done with this section. Make sure you do the homework for it. I will send this out as a document for everyone, and it'll be a mini exam, but I'm going to make it due like, it's not due like next week. It'll be a few weeks before it's due. All right. So you can kind of chip away at it. And that's it. I'm gonna put you in breakout rooms, and at 2:40 we'll stop. Okay. Any questions before we do this?